Hi everyone, this is Mrs. J, and today we're going to talk about separable differential equations. All right, I have a couple warm-ups for you guys, so here is the first one. So go ahead and pause the video and give it a try. All right, go ahead and check your work here. So I made some tables just to help me keep track of my slopes. So you can see I have the 4 values for y equals 0, then y equals 1/2, then 1, then 3/2. And then you could see that for y of 0 equals 1, you start at that coordinate and then you follow your slope field to make your graph. All right, here's another one for you to try. So again, please pause the video and give it a shot. All right, go ahead and check your work here. So for us to verify this general solution, we do need to take y and define y prime and y double prime. So we can substitute y double prime here, and then we'll substitute y right here and verify that it is in fact equal to 0. And here you get 0 equals 0, so that shows this is a general solution. So to find the particular solution, we have to use the given information. So if you substitute x equals pi over 6 and y equals 2, it allows you to solve for C1. And if you substitute x equals pi over 6 and y prime equals 1, it allows you to solve for C2. And then you substitute those in to give you your particular solution. All right, so today we're going to start talking about separable differential equations. So a separable differential equation is just a first order differential equation where dy dx can be written as the product of a function of x and a function of y, or the ratio of a function of x and a function of y, like this. So that's the start. And it is something that can be rewritten. So all of the terms or factors involving y can be placed on one side, and all of them involving x can be placed on the other. So a separable differential equation, you need to be able to actually separate the two variables onto two separate sides. So if you look at this first form here, dy dx equals g of x times f of y, we could actually take this dx, multiply it to the right side, and take f of y and divide it to the left side, and we could write it like this: 1 over f of y times dy equals g of x dx. So we could see that all of the y's are on one side, all of the x's are on the other. So this would be considered a separable differential equation. Same thing for this second form. We could say h of y dy by multiplying this to the other side equals f of x dx. So again, we have the y's on one side, the x's on the other. So this is a separable differential equation. All right, so here we're going to look at a few different differential equations and see if they can be separated. So if you look at this first one, we could see this is a function of x and a ratio of a function of x and a function of y. And we could see that by multiplying, we could rewrite this as 3y dy equals x squared dx. So yes, this is a separable differential equation. All right, let's look at part B. So here, we want to see if we're able to rewrite this maybe as a product of two functions of just x and y. So we have two options that we could try. We could try factoring out a power of x, but when you do that, we still have a function of x and then a function of x or y, or if we factored out a power of y, which is all we can really factor out, we would have xy minus 2x squared. So there's no way to create just a product of a function with just x and just y. So this one would not be separable. Now if you look at this next example in part C, here it's just a function of x. Here it's x times y. So if we do a little bit of reworking, it is possible to put all of the x's on one side and all of the y's on the other. So here I'm going to divide this y over to the other side, so 1 over y dy. We would always like to keep it dy and then just dx, so not like 1 over dx for our final separable equation. And then on the right side, I'll keep the x where it is, and then I can divide away this binomial. And then I have this dx, which I can also multiply to the other side. So dx. So we could see that, yes, this one is separable. All right, looking at example 4, or part D. Here we have a function of y and a function of x, the ratio of these two separate functions. So here we can keep the 1 over x here and move this to this side. So on the right side, it'll be 1 over x dx, and then we can take e to the y plus 1 and divide it over to the left side. So 1 over e to the y plus 1 dy. So you can see that, yes, this one is also separable. And then for our last one, this kind of looks like part B, but you'll see for this one, if we actually, you see that both of these terms have y squared. So we can actually factor out y squared altogether, like this. And so this now is the product of a function of y and a function of x, and they are separate. So we can divide by y squared, so 1 over y squared dy, and then we'll keep that x minus 2x squared where it is and move the dx to the other side. So yes, this one is separable. So just because it initially doesn't look like the correct form for a separable equation doesn't mean that it's not. So in this case, you can see it's a little different than part B. You can actually separate the variables. All right, so now we're going to be solving first order separable differential equations. So first, we need to make sure it's a separable differential equation. And if it is, we're going to rewrite the function with the function of y times dy on one side and the function of x times dx on the other side. So we are essentially going to separate, just like we did in the last examples. And then once they're separated, we're going to integrate each side. So we're going to integrate y with respect to y and x with respect to x. And then once we've done that, we'll finish solving for y. We're going to isolate y if we can. Sometimes we aren't able to actually do this. So sometimes we end up with an implicit equation. So an equation that's in terms of x and y, and that's okay. But also note that this will always give us a general solution, so we should have that plus c. So unless we're given more information, it will be a general solution. All right, let's try this first one together. So here we do have a separable differential equation. So we're going to start by separating our variables. So we end up with 3y squared dy equals x squared plus 2 dx. So now we're going to integrate both sides with respect to the given variables. So we'll do the integral of 3y squared dy and the integral of x squared plus 2 dx. So this would give us y cubed plus c, I'll call it c1. So we have a constant of integration on the left, technically. And then we have 1/3 x cubed plus 2x, and then I'll say plus c2 here. And now we're going to see if we can continue solving for y. So I'm going to subtract this c1 to the other side. So when I do that, we end up with c2 minus c1. So we can just write this as c. So c kind of encompasses c2 minus c1. And then here to finish solving for y, we can just take the cube root of both sides. So cube root of everything. So the cube root of x cubed over 3 plus 2x plus c. And the c, your constant of integration should be within your cube root. So notice that this is a general solution to our differential equation. All right, let's try another one. So let's start by rewriting it. So we have 1 minus y squared dy equals x squared dx. And then we can integrate both sides with respect to their respective variable. So here we get y minus 1/3 y cubed. And again, I'm just going to do a single c on the right side of my equation, equals x cubed over 3, or 1/3 x cubed, and then plus c. And then from here, we would try to isolate y as much as we can. I mean, if you want, you can rewrite it like this. So we could say 1/3 x cubed plus 1/3 y cubed plus c, but there's no way to fully just solve for y and have it say y equals without a y on the other side. So this is an implicit relationship. And in this case, we can actually just leave our answer like this or like this. Because, again, you can't fully solve for y, and that's okay for problems like this. All right, so let's try another one together. So here, when I separate this differential equation, we get 1 over y dy equals 1 over 2 plus x dx, and then I can integrate both sides. So on the left, we get the natural log of the absolute value of y, and on the right, we would get the natural log of the absolute value of 2 plus x, and then I could just have a single constant of integration on the right. So now I want to try to solve for y, and I can for this problem. So we are going to need to start by rewriting this in exponential form. So we have base e, and then to this power will equal the absolute value of y. So absolute value of y equals e to the power of natural log of the absolute value of 2 plus x plus c. From here, we're just going to kind of chip away at simplifying. So for this, I do want to be able to simplify this e to the natural log of absolute value of 2 plus x, but I do need to separate these two terms. So I can rewrite it like this: e to the power of c times e to the power of natural log of absolute value of 2 plus x. Now this, if c is a constant, then e to the power of c is also a constant. So I'm going to actually give it a new variable. I'm just going to call it k, just to help us simplify it a little bit. So we get absolute value of y equals k, and then this, since we have base e and base e, this will just simplify to absolute value of 2 plus x. Now, to help us get rid of this absolute value, here we can do a plus or minus on the other side, so to take into account all the times when what's within your absolute value is positive and negative. So we could say y equals the plus or minus k times the absolute value of 2 plus x. And then from here, it gets a little bit funky. So this absolute value, so we know that there's the positive and the negative values within it. We can say that the absolute value of 2 plus x is just plus or minus 2 plus x. So it's the positive, whatever 2 plus x is, the positive version of that and the negative version of that. So this plus or minus here and this plus or minus here, they can all kind of get absorbed into k, because again, k is just a constant, and it can be positive or negative. So all of our plus or minuses get absorbed by k. So our final answer, most simplified, is just going to be k times 2 plus x. So definitely a little bit different. The solving is a little bit tricky, and then kind of understanding that all of these different things that we're working with this e to the c and different absolute values can all just be represented by a single constant, which we'll just call k. All right, we're going to try one more together. So here we do have a separable differential equation. So let's separate it. So we have 2y minus 2 dy equals 3x squared plus 4x plus 2 dx. Now from here, let's integrate both sides. So that leaves us with y squared minus 2y equals x cubed plus 2x squared plus 2x plus c. So first we are going to finish solving for y. We can actually isolate y in this case, but first let's use this extra piece of information to help us find our c value so we can have a particular solution rather than a general solution. So remember, this is just saying when x equals 0, y equals -1. So we can substitute those values. So -1 squared times 2 times -1 equals 0 cubed plus 2 times 0 squared plus 2 times 0 plus c. So we can see that c is just equal to 3. So then that leaves us with, let me write it over here to the right. Y squared minus 2y equals x cubed plus 2x squared plus 2x plus 3. Now, from here, all we have to do is try to isolate y. And in this case, we actually can. We are going to need to complete the square for y to help us solve. So I'm going to find my magic number. I'm going to take my b value, divide it by 2, and square it. So I'm going to add 1 to the right and the left side of my equation. And then the left side becomes y minus 1 squared. The right side is just staying the same. Well, I'm going to combine like terms. And then I can take the plus or minus square root of both sides. And then I can just add 1 to both sides of my equation. So I'll write it out front. 1 plus or minus the square root of x cubed plus 2x squared plus 2x plus 4. So nothing too crazy here for solving. It is good to remember that for something like this, we can solve for y by completing the square. But here we have a particular solution, again, because we had that extra information which allowed us to solve for our c value. Okay, here's our last example for today. So go ahead and pause the video and give this one a try. All right, go ahead and check here. So first you're going to separate your variables, and then we'll integrate both sides. Here, to help us integrate, we'll definitely want to split up this into 2 terms. And then we get the natural log of absolute value of y plus y squared equals sine of x plus c. We use that extra piece of information to help us find c, giving us a particular solution. And notice this did say you can't solve for y, so we do have an implicit answer for this equation. All right, that is all for today's video. Thank you so much for watching.